Hello, in this video I'll be discussing basic quantum mechanics and how they apply to quantum computing. This might get a bit confusing, but bear with me and let me know if you have any questions in the comments and I'll do my best to answer them. Thanks. First, let's discuss some characteristics of quantum objects that are pretty fundamental to how they function. A phenomenon in quantum mechanics that is absolutely critical to how quantum computers function is interference. When waves combine, either constructive or deconstructive interference is the result, unless the waves are identical. In constructive interference, when the waves are combined in such a way that the crests of the waves are close to each other, the overall amplitude will increase. On the contrary, if the troughs of the wave are close to the crests of the other, they will kind of cancel each other out and make the amplitude of the wave smaller. In summary, interference is the idea that these waves in quantum mechanics can be used to modify each other. How do we know that quantum objects even work like waves, though? Quantum objects have a property called wave-particle duality, and I'll briefly explain how this property was initially discovered, iterated on, and proven. Prior to the 19th century, it was debated whether quantum-level objects such as light existed as a particle or a wave, and many famous physicists such as Isaac Newton were involved in this debate. Eventually, Thomas Young performed the famous double slit experiment in the 1800s. If you're not sure what this experiment was, it basically proved that light interfered with other sources of light, the same interference that we previously discussed. This led to the belief that light was purely a wave. I'll provide a link that describes this experiment a bit more in depth if you're interested. If light was solely a wave, though, that would mean it needed to travel through a medium, like a normal wave. This gave scientists the wrong idea that there may be a special medium just for light, even though that we now know that light can travel through a vacuum. So how is that possible? In the 1900s, Albert Einstein hypothesized that light consisted of small bundles of energy, which would later be named photons, and he believed these photons moved in a wave-like motion. In the 1920s, Louis de Broglie was finally able to prove that light, and therefore other quantum objects, had properties of both waves and particles. All of the research and discovery done by these people allow us to understand the properties of qubits and work with them. Because they have wave properties, they can be subject to interference. This allows us to create superposition and entanglement among qubits, both of which I'll explain shortly. Superposition and entanglement are fundamental to quantum computing, so understanding the properties that allow them to work is key. As I discussed in the previous video, superposition is also a concept that really differentiates qubits from classical bits. Last time I described it as the ability for a qubit to be in multiple states at once. I'm going to explain it in a bit more depth now. The easiest way to represent superposition is, and what it means, is with a state vector. State vectors are pretty much what they sound like, vectors that contain all of the possible states for a qubit or quantum circuit. More specifically, a state vector contains probabilities for each possible state of a qubit or a qubit system. And this is going to help us kind of break down qubits with different superpositions and all of their probabilities. For example, a state vector for a qubit might be just a simple 1, 0. This indicates that there is a 100% chance that when the qubit is measured on a classical bit, it will be in the 0 state, like the classical state. A state vector of 0, 1, on the other hand, would mean that it is guaranteed to be in the classical 1 state when measured. And in a case where the measurement of the qubit is not guaranteed, there might be a state vector of 1 over square root 2, 1 over square root 2, which means that the qubit has an equal chance of being measured as 1 or 0 on a classical bit. And so there's a lot of different possible superpositions, well, infinite, but this is how they're represented and in a mathematical way, and this is a much easier way to look at them, in my opinion. Another quantum mechanic that is integral to quantum computing is entanglement. When a qubit is entangled with another, it means that their states are connected. For example, let's say I have two qubits that are entangled. One possible way that they might be entangled is that when qubit A is measured to be in the classical state 0, qubit B will always be in the classical state 1, and when qubit A is measured to be in the classical state 1, qubit B will always be in the classical state 0, so they always kind of have to be opposite one another, and we can force them to do that. This seems pretty simple at a high level, right? And it's much easier to understand than some other things in terms of just the outcome of it. The qubits can also be forced to be similar, so maybe they always have to be 0 and 0 or 1 and 1. Entanglement is a big part of what allows quantum computers to be so much faster at certain problems than classical computers, as on qubit can be used and connected to many, which creates lots of possibilities. That sums up most of the basic quantum concepts that are necessary to understand quantum computing at a basic level. In the next video, I'll speak more about quantum circuits and how these mechanics can actually be used in software and in circuits. Thanks for watching.